this problem, we're going to be looking at rigid body equilibrium. And by rigid body, we mean that although we've drawn somewhat of a truss here, we're not considering any of the internal forces or the internal stability or determinacy of this truss. Rather, we're looking at it as a single object that is rigid, and we're trying to determine the reactions. Part 1 of this problem, or part A of this problem, is determining whether it's determinate and stable. Part B is find the reactions at A and B. So, as always, the first part of any problem will be step 1. Draw the free body diagram. Now, a free body diagram simply simplifies our problem down into something that is only containing the information that we need to solve it, the forces, the directions, and the dimensions that are necessary to determine all the unknown information. So we draw our geometry in. We draw in our known force values in the direction that we know them. So we're drawing this F3 force in as a negative force because we know it goes that direction. F4 goes at a 45-degree angle to the horizontal. F1 acts downwards, and F2 also acts downwards. Our unknown values for this problem are our reactions. We have a vertical reaction at B. By is unknown, and it's acting in a direction that is perpendicular to the surface. We have a roller support, and roller reactions happen only in the direction perpendicular to the surface. On this side we have a pin support. A pin reaction happens perpendicular to the surface and parallel to the surface, or actually any two orthogonal directions. So here we're going to draw them as AY and AX. We'll add in some of our dimensions. meters. And you might have noticed that everything except for F4 is written in terms of Cartesian force components, so X and Y forces. F3 is an X force, F2 is a Y, F1 is a Y, and then our reactions are in components. So we can break our force vector here down into two force components, F4X and F4Y. And we can solve for these. F4Y is equal to F4 sine 45 degrees, and this is equal to 3.536 kilonewtons. And we could say that F4X is also equal to 3.536 kilonewtons if we did the same math. It's at a 45-degree angle, so the X and the Y components are the same magnitude. At this point, we have all the necessary information in our free body diagram, and we're ready to move on to solving part A of this problem. Is it determinate, and is it stable? So step 2 is determinacy and stability. So we know that a rigid body is determinate if, or its degree of indeterminacy is calculated as the number of reactions minus 3. When we get into trusses and beams and frames, this becomes a little bit more complicated as we start to explore internal problems within the beam, so internal releases of member forces and things like that. But for now, it's simply a matter of determining how many external reactions we have, AY, AX, and BY. So here we have 3 minus 3 is equal to 0. This is determinate. So since it's determinate, it means that we can solve this problem using the equations of equilibrium that we know. If it was indeterminate, in other words, if it had more reactions or more unknowns than we have equations of equilibrium, 3, then we would need to introduce new equations to be able to solve that. And that's outside of the scope of this course. It's possible, but it's somewhat more difficult. So the next check is for stability. And here, external stability, we're checking to see whether or not we can satisfy equilibrium in all directions. The first check we can do is say that SI has to be greater or equal to 0. And since we have 0 is equal to 0, greater or equal to 0, we can say that yes, that's okay. If we didn't have that, we'd have insufficient reactions and we'd have a stability problem from that. Now we can say that not all reactions are parallel. So we have BY, it's acting in the vertical or the Y direction. We have AY, it's also acting in the vertical or Y direction. In other words, it's parallel to BY. However, AX is orthogonal to those two. It is perpendicular to AY and BY, so they are not all parallel. If they were all parallel, then we would not be able to satisfy a sum of forces in one of the directions condition. And second of all, not all reactions are concurrent. So here we have AX and AY meeting at A. However, BY is parallel to AY and it never actually meets AY or intersects AY. So we don't have a point of concurrency, so we're fine. And this concurrency check is to see if there is some moment equilibrium ability of this rigid body. If all reactions met at the same point, then there would be no possible way to satisfy moment equilibrium. So at this point we're done. Part A, the rigid body is determinate and it is stable. And now we'll move on to determining the reactions. So to find the reactions, we call this step 3. We're going to apply equilibrium. And as we recall, we have 3 equilibrium conditions for planar structures or for rigid bodies in an xy plane. We have sum of forces in x has to equal to 0. Sum of forces in y has to equal to 0. And sum of moments about any point in this xy plane about the z-axis has to equal to 0. We'll just box those because they're very important equations that we'll use throughout this process. To start, let's pick the easy one. Or actually, you know what? I'm going to suggest we draw this diagram again on this page. We can draw it small, just so that we can see what our forces are and where they're acting. So we have a force here and a force here, and this is F4x, that's equal to 3.536, and this is F4y, it's also equal to 3.536. We have F3 is equal to 5. We have F1 is equal to 8, and F2 is equal to 3. And then we have our unknowns. We have BY, we have AY, we have AX. Beyond that, we can add in our dimensions. 2 meters, and we have 2 meter spacing between these forces here. Okay, so now that we have that drawn again, we can easily reference it as we're doing our equilibrium calculations. So first, let's apply what might be considered our easiest one. Let's do sum of forces in X is equal to 0. And here we can say that if we add up all the forces in X with positive going to the right, and let's draw in our positive coordinate system here just so that we have a frame of reference. Here we have X, we have Y, we have moment and rotation here. So if X force is going to the right, it's positive. If a Y force is going up, it's positive. And if a moment is acting in the counterclockwise direction, it's positive. Also, if an angle is acting in the counterclockwise direction, starting at the X plane, or X axis of the XY plane, then it's positive, starting from 0. So once we have that identified, we can add up all our forces in X using our appropriate sign. We can say that first off we have AX, and we'll write that in as a positive value because it's acting to the right. To that we will add negative F4X acting to the left, and F3 also acting to the left. And that, the sum of all forces in X is equal to 0. We can plug in our values, and we can say that AX minus 3.536 minus 5 is equal to 0. And now we're left with AX is equal to plus 8.536 kilonewtons. Now, this plus value means something to us. Since we're following our positive XY coordinate system here, if a value comes out as positive, it means it's drawn correctly. And since we drew it as a positive value initially, it means it's a force acting to the right. Now, let's try and consider equilibrium in the Y direction. And if we are astute here, we might not do this step first, because we'll soon see that we can't directly solve for our forces in the Y yet, and we'll have to introduce a third equilibrium condition first. But let's try it out. We can add all our forces in the Y, AY acting up, so it's positive, plus BY also acting up, so it's positive, minus F1 minus F2 minus F4Y is equal to 0. All three of these are acting down, so they're negative. And if we go a step further, we can say AY plus BY minus 8 minus 3 minus 3.536 is equal to 0. Or, let's do it over here, AY plus BY is equal to 14.536 kilonewtons. So this is what we said earlier. We have two unknowns in this equation, and we can't go any further with it in this state. So this is where we need to introduce our third equation of equilibrium, which is sum of moments about any point on this XY plane is equal to 0. So we could take it about a point that's off of our rigid body, but there's not much sense in doing that. We should be strategic when we take it. If we take it at a point such as A or B, then our force BY or force AY will intersect with the point about which we're taking moments. In other words, the moment arm at that point will be 0. If the moment arm is 0, it does not contribute to the moments, and it will be eliminated from our equation, and we can directly solve for the other unknown. So that was a bit of a long statement, and let's put it in action and see what we can do. Let's take sum of moments about A and set that equal to 0. So here we're going to be looking at force times distance. And remember, the distance is that is orthogonal to the line of force that passes through the point at which we're taking the moment. In other words, the perpendicular distance to the point about which we're taking the moment. To do that, let's begin with putting in our values, and then we're going to assign a sign to it. So if we're taking a moment about this point here, and we're looking at F1, well, F1 has a 2-meter distance to it, to be perpendicular. 2-meter distance to the line of action that's perpendicular to the line of action. And if we were to pin it, if we were to stick a pin in the paper and hold it at that point, and then rotate the paper according to this force, we would see that this is acting clockwise. It's putting a clockwise moment on this, and we define clockwise as negative, so we add a negative sign to that. And the same thing happens with F2. The moment arm is longer, but it still produces a negative moment, so it's minus F2 times 4 meters, also acting in the clockwise direction. To that, we will add a negative F4y. Now here, if we take F4y and we extend the line of action of its force down until we get a point that is perpendicular to A, where we're taking our moment, we can see that the moment arm for F4y is also 2 meters. However, and also it is acting in the negative direction. Now, if we look at F4x, the moment arm for this one, if we extend the force line, extend the tip and tail of this force until we can find a point that is perpendicular and passes through our point about which we're taking our moment. And we can see here that this moment arm, F4x, is also equal to 2 meters. And this moment is a positive moment. It's trying to rotate this rigid body counterclockwise. In addition to that, we have F3, and we can do the same thing. We can extend the line of action of F3 until we reach a point that is perpendicular, that extends through the point about which we're taking the moment. And this has the same moment arm as F4x. And it's also a positive moment. And finally, we have one last moment term. We have By. And By also produces a positive moment, and our moment arm in this case is 2, 4, 6 meters. And all of that is equal to 0. Sum of moments is equal to 0. Now, it strongly suggests that you draw these little curly cues on top of your force component times your distance, and this will allow you to easily double check that you're adding or subtracting your moment contribution appropriately. If you don't have them up there, it can become very difficult when you have an equation that is 6 terms long to determine this is acting positive or negative. So it's a simple process where you add that component as you're writing in the parts of the equation. Now, if we start to plug in our values into this equation, we can see that we have minus 8 times 2, minus 3 times 4, that's F2, F1 is 8, minus 3.536 times 2 plus 3.536 times 2 plus 5 times 2 plus, and I should have maybe written the By term in blue, just trying to differentiate our variables from our known values. By times 6 is equal to 0. And if we just add up all the things that we can and divide by 6, we can say that By is equal to plus 3 kilonewtons. Since it's a positive value, it means that we drew it correctly, and it's a force that's acting upwards. Now that we know By, we can go back into this equation. So let's call this equation 1. So we're going to take the next step is to sub By is equal to plus 3 into equation 1. Now, if we were smarter when we were doing this problem originally, we would have done the sum of moments first. And now we would have begun with sum of forces in y, and we would have only had the one variable ay. But it doesn't really matter. We've gotten to this point already, so let's rewrite equation 1 as ay plus by is equal to 14.536 kilonewtons. And now we can say ay is equal to 14.536 minus 3. And this gives us ay is equal to plus 11.536 kilonewtons. So at this point, we have completed solving for all of our reactions, ax, by, and ay. And each of those reactions were positive values. That means that we drew them correctly in our original drawing. Now we're only left with step 4. This is to draw our summary. So here we draw out our our rigid body, and we're going to want to include all of our force components on this. Now I didn't draw that very well, so let me just scratch that out and we'll go to the next page to do this properly. Alright, so here we're going to draw our summary. And we'll want to draw in things relatively accurately if possible. So that means we'll go up 2, 4, up to here. We'll go over and down. And we've got those vertical members. And now we can say that we had 5 kilonewtons acting at 45 degrees. We had 5 kilonewtons acting horizontally. We had 8 kilonewtons and 3 kilonewtons. And then we went ahead and solved for our reactions. We found that by was equal to 3 kilonewtons. ay was equal to 11.536 kilonewtons. And ax was equal to 8.536 kilonewtons. To that we had some quick dimensions. 2 meters, 2 meters, 2 meters, 2 meters. And at this point, we're done the problem after we've completed our summary diagram.